Hi everyone, glad to see everyone. So today we glad to present you this very interesting topic by Liu Yongzan. So Dr. Yongzan Liu is currently a senior research scientist at Schlumberger Dow Research, located in Cambridge, Massachusetts, United States. Before joining as Schlumberger, he was a postdoc research fellow in the Energy Geoscience Division at Lawrence Berkeley National Lab. He has been working on various topics related to energy geomechanics, including coupled thermal hydraulic mechanical modeling of subsurface fractured reservoirs, hydraulic fracturing monitoring and characterization, enhanced geothermal system, system behaviors of gas hydrate accumulations, geological carbon storage. He is currently interested in the integration of advanced numerical modeling and monitoring techniques to better understand the complex processes in subsurface reservoirs. He has submitted 3 patents, co-authored 1 book, and published more than 30 technical papers. He holds PhD degree from Texas Agriculture and Machinery University and master degree from University of Alberta and a bachelor degree from China University of Petroleum, all in petroleum and energy. So very glad. Let me give time to Yongzan. Okay.
Okay. Thank you, Jichuan, for the introduction, and thanks for inviting me to share my recent work with the community. Today, I'm going to talk about quantitative interpretation of low-frequency distributed acoustic sensing data for hydraulic fracture monitoring. In my presentation today, I will cover the following parts. Firstly, I will briefly introduce what is cross-well low-frequency dust and its application in hydraulic fracturing. And then I will present a brief review of the current field data acquired from different formations and the current research efforts in the data interpretation. And following that, I will show you our recently developed a quantitative interpretation workflow. And then I will show you the performance of this workflow using a synthetic case with known reference solution. And after that, I will present a field case from the hydraulic fracturing testset 2 project. So this is a very popular plot. I guess people working on that low-frequency dust has seen this many times. This is a work published by Dr. Ge Jin from Colorado School of Mines. This work was published in 2017, which introduced for the first time the low-frequency distributed acoustic sensing for hydraulic fracturing monitoring. So basically, as you see, the left, which is a schematic of the well configuration and the monitoring stuff. So if we install fiber along an offset monitor well, and we inject laser pulses continuously down to the fiber, and when we do the stimulation job on the treatment well, the fiber could detect the fracture-induced rock deformation by the relay scattering. So this the red plot shows the data monitored from this fiber during the stimulation job. As you can see, there are some very classical signatures that can help us to characterize the fracture propagation process. So basically, in the fractured zone, which is the treatment interval, we usually have these extending signatures labeled by this red color. And on the zones that is outside of this treatment interval, we usually have this compressing signature, which is corresponding to the stress shadow region, which is we usually use this term in hydraulic fracturing community. So once the injection stops, we observe some polarity flip. So the region, so during the stimulation stage, the region that experienced extending signature now shows this compressing signature. And on the contrary, this stress shadow region shows a relaxation signature indicated by these extending red colors. So by that time, the authors, Jin and Roy, hypothesized that these extending and compressing signatures are directly related to the fracture propagation and the final fracture geometry. However, at that time, no detailed quantification has been achieved to relate the fracture geometry and to this string data set. But after this initial discussion in 2017, in the past 7 years, which is relatively a short period of time, this technology has been used in different formations across the globe. So in United States, almost all the major unconventional reservoirs has been using this technology to monitor their stimulation jobs, including almost all the major formations in United States. And also in Canada, the major unconventional reservoir, Montany, also installed a lot of fiber in their wells. And recently, China also started to use this technology to monitor the hydraulic fracturing process. And this review is based on the public data. I believe there are many more other use cases that has not been published. From this review, you can see this technology is pretty, it is increasingly popular. And I believe a lot of jobs will adopt this technology to monitor the stimulation job. And more recently, there is another application in a different setting, which is enhanced geosystem. So the FORGE project and the Fervo Energy, they already successfully acquired many low frequency dust data during the stimulation job in the extremely hot reservoirs. We already got a lot of high quality data, but how to interpret this data is still the research activity is still in the very early stage. I classified the current research efforts into 4 categories. So the first one is field data analysis, which is of the very basic analysis, I would say. So if you got data, you just plot them in different forms. The most popular one is the waterfall plot. So by visualizing the data, so by reading the plots, you can already got a lot of information. For example, where is the fracture height? What is the fracture propagation direction? And if you have like fluid leak off into the previous stage, those kind of things, you can get this obvious information very easily. And the second direction is the forward modeling. So we cannot just qualitatively analyze the data by plotting them, right? We need to understand the driving mechanisms or the influencing factors for the observations. So by utilizing fracture and geomechanical modeling, we can generate some synthetic data that matches the patterns of the field observation. So we can get some better understanding of the driving mechanisms for the observations. And there are also some lab experiments being conducted, has been done. The purpose of these lab experiments is mainly to prove that our hypothetical, the hypothesis we obtained from the forward modeling, or the conclusions we obtained from the forward modeling is consistent with the observation, is consistent with the field observations. So a few lab experiments has been published. So their experimental results under the hypothetical conditions are pretty consistent with the field observation. So this gave us insights that our major interpretation for now should explain a majority of the patterns observed in the field. And the last part is inverse modeling. I guess this is the most exciting part to me because this part would let the measurement itself to tell us what happens in the subsurface. So without, of course, to do the inversion appropriately, we need to develop some advanced inversion algorithms, so we can get some valuable and accurate inversion results. Otherwise, if we don't have an appropriate inverse modeling, we may get some misleading conclusions as well. So we need to be very cautious on this. And previously, the inverse modeling part, the published research has been focusing on the data after fracture heat. And there has very limited study focusing on data for the whole data monitored during the whole treatment period. So in this workflow I'm going to present today, we focused on the data for the whole for the whole period of a fracturing job, but we divided the data at the fracture heat time because before fracture heat and after fracture heat, the data are sensitive to different physical processes and fracture parameters. So we found that before fracture heat, the data basically is a hard shape. This hard shape data is mainly controlled by the fracture geometry near the fracture tip region. So I will show you how we got these conclusions through the cases. And for this part, we focus on the inversion of the fracture tip advancement, which basically the fracture half-length evolution and the fracture propagation velocity. And after fracture heat, our previous work has proved that this data, mainly the data from the stress shadow region, is mainly influenced by the fracture geometry in the vicinity of the monitor well. So after fracture heat, we focus on a local fracture geometry evolution. This is parameters, the primary parameters we identified at different time interval. So we made some assumption on the other parameters that are less sensitive to the measurement. So in such way, we can simplify our inversion algorithm while maintaining a high degree of accuracy. So you will have a better sense of what I explained here as we dive into the case studies. So the first thing we need to develop a forward model that relate the fracture geometry to the low frequency dust data. So here we used the widely used method, which is called the displacement discontinuity method, to build the forward model. In a concise form, the string can be expressed as a G matrix by the fracture width. And this string, we use this definition because we want to honor the spatial resolution of the dust data. So we didn't calculate the string by the gradient of displacement, but we use this displacement difference over a certain distance. This parameter is called gauge length. So it represents the spatial resolution of the data, which is usually 5 or 10 meters. So that our calculated string is equivalent to the string at a certain spatial resolution. And this G matrix is a function of the fracture height and the fracture length. So all the 3 parameters is included in this geomechanical model. So we can, so through this model, we build a direct relation between the string and the fracture parameters. So as I just mentioned, we divided the data into 2 sections. So the first one is the fracture is before the fracture heat. So as I just mentioned, for this part, we focus on the fracture geometry near the fracture tip region. So as we know, in the fracture tip region, there's usually a sharp fracture width variation. So we need to discretize the whole fracture into several sub-elements so we can capture the width variation in the tip region. And we further assumed a width distribution along the fracture. So for example, here we assumed elliptical shape, and we expressed the width distribution as a function of the fracture width at the perforation point. And we use this shape operator to calculate the width distribution along all the fracture elements. And the objective function, of course, is the strain differences between the calculated strain and the field data. And after fracture heat, previous study has proved that the data is only sensitive to a fracture geometry within a certain range near the monitor well, regardless of how complex the whole fracture is. So by that data sensitivity, we proposed an equivalent fracture concept. So we use one single fracture element with an equivalent fracture width and height to represent the fracture geometry around the monitor well. So which is labeled by this, the red color here. So by doing this, the inversion parameter is reduced to 2 parameters, which is the fracture width and the fracture height of this single element. And of course, the objective function is also the difference between the calculated strain and the measurement strain data. So by minimizing this error, we can get the inversion result of the model parameters. So that's basically the whole idea of the inversion algorithm. So we adopted this synthetic case from our previous paper to test the performance of this algorithm. In essence, we run a fracture propagation simulation. So we know how the fracture propagates and all the fracture geometry parameters. And we monitor the data along these monitor well locations that is 100 meters away from the treatment well. And the data is shown in this plot. And this is the data we used for our inversion results. So let's focus on the part that is before fracture heat. Before fracture heat, as I just mentioned, we focus on fracture half length and fracture width distribution. And since this is a static process, right, but it's time serial, so we know the fracture half length at each time step. So we calculate the velocity using the length increase over the time step. So you can see our inversion results indicated by these dots matches pretty well with the reference solution, which is the simulation results. And the data or modeled data are very consistent with the input data. So this shows at least our inversion results captures correctly the fracture propagation patterns. But when you look at the fracture width distribution, you would realize that there are very obvious deviations, especially at the later time, because as I just mentioned, in our algorithm, we assumed we predefine a width distribution along the fracture. But when our assumed shape is different from the reality, so our inversion result you would expect some difference. However, when you look at the strain data, especially I plotted the strain data at these 3 time steps. Even when we have obvious difference between our inversion results and the true solution, our strain data still got a very, I would not say perfect, but we got a very decent match of the strain data, which means our inversion results is one realization that could generate this strain profile as well. But the reality is also we cannot fully capture the whole fracture width distribution in those later times. But when you observe all these time steps, you would observe one consistent behavior is that near the fracture tip region, our inversion results show a very decent match with the true solutions, which means if we got the fracture tip region matched, we could get this string data matched. And in another word, if we without any a priori information on the fracture geometry, by inversion of this string data, we can only get a good estimation of the fracture geometry around the tip region. So through this analysis, our conclusion is that without any strong assumptions, using the data before fracture hit, we can have a decent or a very reasonable estimation about the fracture tip behavior. After fracture hit, we focused on the fracture geometry around the monitor well. So we used the equivalent fracture, which I repeated again. So we used a single fracture to represent the fracture around the monitor well. So for example, at the last time step, we know from the simulation the true fracture width and height is these values, and we compare our inversion results to the true solutions. And this plot shows the details of the iteration process of one inversion at a single time step. You can see for both the height and the width, the inversion, the iteration or the inversion converges is very fast to the true values, indicated by this red line here. It only takes less than 100 iterations. And this is plotting in another form. You can see the search path is pretty clear and straightforward. And this string reduction, the string difference between the simulation and the input data reduces very quickly. And after about 60 iterations, the difference already becomes very negligible. So this shows the inversion algorithm is pretty converges very fast. And we repeat this, and then we plot all the final models. And we want to see what the distribution looks like for the all the models that converges. From the distribution, you can see the distribution is pretty close to normal distribution, and with the mean value is pretty close to the true values, which is indicated by this red triangle here. And also, the difference between the lower bound and the upper bound of the final models is pretty limited. So the width range is less than 0.1 millimeter, and the height is less than 0.5 millimeter. And the result indicates that the inversion results, the uncertainty of the inversion result is also pretty low. So we can, but when we did this research, we tried to see how the distribution looks like. So we used a stochastic inversion algorithm, which is Markov chain Monte Carlo based. So it's computationally consuming, but if we know this is the distribution is pretty normal and the uncertainty is pretty low, and there is only one global optimum, we may use it may be better to use like gradient-based inversion algorithms, which could be more computationally maybe computationally efficient. After we tested the algorithm using a single time step, we repeat the same procedure to all the time steps after fracture hit, so we can get an idea of how the fracture evolves. And as you can see, for all the for the whole time period, our inversion result matches pretty well with the true solutions, except for the very early stage, right after fracture hit. This is because our assumption does not hold for this period. And this is why I keep emphasizing that assumption really matters in inverse modeling. If we don't make the reasonable assumptions, we may get very misleading interpretations. Because we assumed an equivalent fracture, right, around the monitor well. So when the fracture just approaches the monitor well, which means it's the fracture tip region near the monitor well. So our assumption is evenly distributed around the monitor well. That assumption does not hold. So we don't get a very reasonable match to the true solution. So, but once the fracture propagates further and our assumption becomes valid, our inverse result show a very good match with the true solutions. So here is also there are some room to improve these algorithms, but here our recommendation is that you can apply this algorithm after a short period of time after the fracture hits the monitor well. So the overall through this synthetic case analysis, our inversion algorithm performs very well for both before and after fracture hit. We focused on different fracture parameters at these two different time intervals. So now we are ready to apply it to the field case. This is the field case we from hydraulic fracturing testbed 2 project. This is a single fracture propagation case, which is pretty good because we eliminated the fracture interactions, and this is a really good case to test our invariant algorithms. The stimulation job is conducted on this B4H, and we monitor the low frequency dust data from an horizontal monitor well, which is B3H, and the data is shown here together with the pumping curve. As you can see, for this is a scientific stage. So they designed one fracture, and they also conducted some injection interference test. So they lower the rate and increase the rate, and they conducted this for 2 cycles. And you will later on, I will show you how the fracture evolves corresponding to this interference. And this is the data from the horizontal well is the data that we work on, which means we will conduct inversion on this data. And luckily, we have another monitor well, which is the B5H, which is a vertical monitor well, and the data is shown on this plot. And this data, we use this data to validate our inversion results because you can see this transition from this red color to this blue color, and this boundary here actually related to the upper and the lower bound of the fracture in the fracture height direction. So basically, these transition zones can roughly tell us how long is the fracture. So what is the value of the fracture height? This is a very valuable resources for us to validate our inversion results, which I will show you later on. So this is a very good case for scientific studies, and we chose this because we have some additional information to validate our results. So now let's focus on we divided into 2 parts. We talk about the time interval before fracture hit first. So this is our inversion results. The blue squares is the fracture half-length evolution, and this red squares is the velocity we calculated by the length increase between time steps over the time step. So you can see initially the fracture propagates continuously, and later on it becomes a intermittent pattern, and it propagates suddenly and stop. There is a quiet period, and then it grows and then stops. We observe this a very interesting pattern, and at this time, the fracture hit time, our inversion result is exactly the well spacing, which this point can prove to some degree that our inversion result works well, or inversion algorithm works well, and the inverse result is reasonable because you can imagine, right? At this fracture hit time, our fracture half length has to propagate the well spacing distance, right? And we exactly captures this reality. And from the string comparison, you can see overall, our modeled data is very consistent with the field data. And we also plotted some more detailed comparison at 4 specific time steps. And you can see the modeled data matches pretty well with the field data. And I guess this is a very interesting observation. So I also did some literature search, and the previous there are some previously published paper. This one is a numerical modeling work, which supports this intermittent fracture propagation observations. So they did some analysis to explain the physics controlling this observation. And more recently, Harvard published experimental work. So even though at a different scale, but they also observed this stepwise or intermittent fracture propagation behavior. So this throughout a question. So if we need to really need to consider this behavior in our fracture modeling, because in a majority of the available hydraulic fracture propagation models, the fracture propagates continuously. So this direct field observation could give us some insights if we really need to consider this, if we consistently observe these behaviors. Of course, this is only one case, and we need more similar cases to see if we consistently observe this behavior. And I guess from HDF2, there are also some other stages with only one fracture. So I'm currently probably will be doing some additional analysis on more data to see if we can observe similar trait from other cases. But this is a really a good scientific problems we need to work on. After fracture hit, as I mentioned, we focused on a local fracture geometry. So because this is a local measurement, so from local measurement, we can just get a local geometry without additional assumptions. So we applied our equivalent fracture approach to this case, and we get the fracture width and the fracture height profiles. And overall, the trend is pretty consistent with the low frequency dust strain rate patterns. So because the fracture width, the fracture opening closing near the at the monitor well location, it will extending or compressing the fiber. So you can see during this period the fracture width increases, keep increasing, and at the fracture hit location you observe this red color, so which means there is extending happens over there, and in this period we got a relatively stable period or even decreasing a slightly decreasing trend, and you can also observe some compressing signatures in this period. And after the injection stops, the fracture would like show some fracture closure trend, which is pretty consistent with these blue colors at this fracture hit location. So the width trend is pretty consistent with the strain rate patterns, similar to fracture height. They are also very consistent because previously the forward modeling study indicates that if there is a obvious height increase, we could observe some extending signature like near the fracture region. So you can see in these two increasing period, we observe this extending here. And this decreasing and increasing trend is corresponding to the 2 cycles of the interference test. You know, they lower the rate and increase again. So the bottom hole pressure would decrease and increase. And Interestingly, the fracture width does not it was not affected too much by the temperature changes, by the pressure changes, but the fracture height reacts more pronouncedly to the pressure changes in these 2 cycles of the interference test. So we got some reasonable trend, and we got a specific number. But how do we know if our number is correct or not? This is a really difficult question to answer because we don't know what exactly happens in the subsurface. But luckily for this specific case, as I just mentioned, we have additional information. So to test the accuracy of our inversion result, of course, firstly, we need to confirm that our inversion converges, right? So we need to get the stream profile matches get matched to a reasonable degree, which means we need to get our stream profiles matches to the field data. And you can see in general, our calculated stream matches pretty well to the field data for the whole monitoring period. And at these specific time steps, you can see our calculated stream, which is the line plot, matches pretty well with the field data, which are the red dots. And the additional information is that, as I explained in previous slides, we have this low frequency dust data from a nearby vertical well, right? You can see for our the time interval we focused on for our inversion, you can see start from here, the height is almost at this value, and in this period it shows a slight increase, and in this period it shows decrease to this value, and at this period it increased again, and during the once the injection stops, the fracture also shows in the beginning shows a decrease in height and gradually stables to a specific value. So the trend is pretty, our inversion result is pretty consistent with another independent data from another well. So this gives us a lot of confidence in our inversion results. In addition to the trend, the specific value is also very close to what we observed from the vertical monitor well. You see, is about 300 to 200 within this range, and in once it's stable, is about 150 meters, and it's pretty close to our inversion results. So this gives us a lot of confidence in our inversion results. Without this, it is very difficult to confirm the accuracy of the inversion algorithms, and it is with this, it is very easy to convince other people that our inversion results is correct. So in conclusion, that is again, the data sensitivity is very important. So we did a lot of work to analyze this, and we find out that before fracture heat, the data is sensitive to the fracture tip, and after fracture heat, the data is mainly controlled by the fracture geometry around the monitor well. So based on the data sensitivity, we developed a slightly different inversion algorithms before and after heat, but we use the same forward model, which is based on, which is the displacement discontinuity method based geomechanical model. But we use different, slightly different solution strategies to do the inversion before and after heat, and we focused on different parameters. And we, from this specific field case, we observed this very interesting fracture propagation pattern. And this previously we also observed this pattern in numerical modeling, but this is the first field evidence, I would say, to like corroborate that opinion, I would say. And fracture height shows more prompt response to pressure changes for this field case. And basically, this is what I want to share. And the majority of the content today is from these two papers. And I would also recommend interested readers, audience to read our previous paper, because these two papers conducted some more fundamental and detailed analysis on the data sensitivities. And thank you for your attention, and I'm open to any questions.
Oh, okay. Thank you, Yongzan. Very excellent talk. So we collect a few questions. First is from Lee. He asked, where is the location measured for the width and height in your page 12?
Page 12, let me go back to this width and height is at the monitor well location. So this is the case, right? So we have a fracture propagation here, because we keep arguing that the data after fracture hit, which is like this part, this data is mainly sensitive to the fracture geometry around this monitor well. So for this case, we extract the values from the fracture element intersect with the monitor well location.
Okay, I got it. Thank you. But that P3D means in this slide is a pseudo 3D single channel?
Yeah. Pseudo 3D.
That's what. Okay, the close. Okay, got it. Thank you.
Yeah.
Okay, and the two following questions is related to the same page, page 15. One, say, if you had a model with, say, two parallel propagating hydraulic fractures versus a single planar one, would you be able to invert the fiber data to distinguish the correct primary model? And some comment, very interesting to see the height and width perturbations with time. We also saw some star-stop propagation at the Technical University Delft many years ago. Okay, I think it's some comment on their work.
Yeah, okay. I got the first the question. I also can read it in the chat. So
okay.
It is about multiple fracture scenarios. I guess we need to add some more constraints on the model to distinguish the width and the height for individual fractures. We haven't. We're currently working on that, but we previously in my previous paper, in the previous algorithm we can distinguish that. But for now, for this model, we haven't tried on multiple fractures. But I believe it's doable, but under some additional assumptions. So I didn't show here, but previously what we did for now for multiple fracture cases, we lump all the fractures into one equivalent fracture. So if, for example, we have one fracture here for this case, if we have another nearby, what we invert is the sum of the fracture width for all the fractures. So yeah, I guess we will continue working on this to try to like to do in a higher resolution, which means in the cluster level to distinguish the fracture geometry in the cluster level. Yeah, that's doable, but we need to like I said, we need to make reasonable assumptions. Yeah, but for now, for single fracture case, we haven't considered that. Yeah.
Okay, thank you. And Tian Yang from Stanford, he requested you give some explanation on the definition of height. And yeah.
In page 15, this page,
yeah.
Fracture height, what is the definition of fracture height and how do you measure it? For our inversion, so as I guess this plot is more clear. So this is just a schematic. So the fracture, for the whole fracture, the geometry could be very complex. But what we did here in our algorithm is we using an equivalent fracture to represent the fracture geometry around the monitor well. So in our model, we assume the fracture with a height is actually just the height of this fracture element.
Okay.
Yeah,
Thank
I'm
you.
not sure if that's your question. And yeah, this is what we got from our model. And the fracture height from this low frequency dust data from monitor well is this transition lines actually corresponding to the upper and the lower bound of the fracture. So the difference between these two lines actually is related to, or roughly equivalent to the fracture height. So for this case, it's probably about 200 meters. Yeah, there are some modeling work to confirm this mechanism, or the mechanisms for the low frequency dust data from vertical wells.
So
yeah.
You mean that the fracture is 2D, right? Or is along a plane, or?
The fracture is, you can think it's like a pseudo 3D fracture. So it's yeah, it's a fracture plane here with a uniform width and a single height. Yeah, you see here. Yeah.
So the height is the depth of the fracture.
The height is the fracture dimension in the vertical direction.
Oh, okay. Okay.
Yeah.
Thank you.
Okay. If anyone have any questions.
So just curious that there's any influence from the monitoring well to the fracture, or like a fluid intake or loss or nothing, just the monitoring
Here,
or the measuring the height.
Here I think fluid is important as well, because the whole process is driven by the ejected fluid, right? But here now we working on the first order parameters. So we work on string, and the first order influencing parameters is the fracture geometry. And I think, yeah, we need to build more complicated models to incorporate the fluid effects. Yeah.
Okay, thank you.
Yeah, thank you.
Okay. Any further question? If there is no further questions, so Yongzan, I have one questions on slide 15. So slide 15, you present some interesting results, like the positive transition between positive and negative string rate, right? So my question is kind of open, like for the negative stages, in your mind, or there is any proposed physics explanation for this? Maybe you can turn back 1 or 2 slides. Yeah. For this, like the bottom pressure is not drop as fast as the slurry rate, right? But an interest is if there are any physical explanation for this stage that causing low injection rate, but the bottom pressure is comparatively not drop significant.
I don't know. So this is just the measurements in the field, I guess. So they lower the injection rate, and the bottom hole pressure will correspondingly show some reduction. But I don't know why, how much the bottom hole pressure should decrease. I guess it depends on. Yeah, this is just the measurements from the treatment.
Oh, okay. I got it.
Yeah.
Maybe I made a mistake on this. Thank you.
Yeah, but for this case, yeah, they just reduce slightly. Maybe it's also because of the range of the axis.
Okay.
Yeah, it should be. Yeah, it's some like fluid dynamic problems. They should be correct because they measured on site. Yeah, this pressure is reduction is related to the slurry rate reduction. No, this is not because they cannot inject at a constant rate. For these 2 cycles, they did this on purpose. So they just want to see what low frequency dust data we can get if we do some like pressure interference test. So they designed this kind of injection scheme.
Yes.
Yeah.
Thank you.
Okay.
Thank you. So, if any further questions? Okay. If there is no further questions, Wei, shall we call it a day?
Sure. Yeah. Thank you so much, Yongzan. This is really interesting. Yeah. If we don't have other questions, yeah, I would say we close it for today, and then reconvert next in 2 weeks. Yeah.
Yeah.
All right. Thank you.
Okay.